back. In this episode we will extend a little bit the territory, the range of applicability of Sturm-Liouville, or the Sturm-Liouville formalism, Sturm-Liouville theory. In the textbook you will find the theory in section 11.4, 11.5, 11.6. It's called Singular Sturm-Liouville theory. I think that suggests more difficulties than that we will encounter, but we will see that as we proceed. So this lecture is split in two parts. First is this part, which is an introduction, and here's the outline of the full episode. So the plan is to have it in two parts. Now we will lay the foundations, and in the second part we will consider an example, and that is a Legendre's equation, but we will come to that. Now, first of all, the aim of this episode, as I said, is to extend the scope of the Sturm-Liouville formalism, and especially to allow the differential operator that we are working with to be a Fuchsian differential equation that has regular singular points. And if you think back to chapter 5, when we have been working on Frobenius theory, those differential equations were in the center of focus, and the reason for that is that those are very important for practical applications. And so far, chapter 11, we have covered Sturm-Liouville problems, but only regular ones, and then the regular singular points are excluded. And the aim of this episode is to extend the formalism a bit so that we can include those kind of differential operators. And I said the motive for that is that Fuchsian ordinary differential equations with regular singular points are very important for applications, certainly also in aerospace engineering. You might think of Legendre's equation and Bessel's equation. For example, Legendre's equation emerges if you solve the problem of the gravitational potential using separation of variables. Then one of the differential equations, namely the one that describes the potential as function of the angles, so the north-south angle of a planet, and also along the equator, the longitude, so the longitude and the latitude, that is the potential depends on those angles according to the general Legendre's equation. And if you would simplify the problem and ignore the dependence on the longitude, you end up with ordinary Legendre's equation. That will be our example in part 2. And then Bessel's equation emerges in aerospace engineering if you work in polar coordinates, typically for wave problems or vibrations or heat, time-dependent heat diffusion in polar coordinates. So what is the plan for this episode? Well, we will carefully revisit the proof of self-adjointness that was central to Sturm-Liouville theory. The property of self-adjointness is central, as we saw in the previous lectures, but we will revisit very carefully what it depends on. So under what conditions is that property available? What is that founded on? And the question is, can we relax those conditions a little bit so as to allow for regular singular points in the differential operator? So that is what we will do in this part. And then in part 2, once we have established those results, we will consider an example, and that will be Legendre's equation. And I can already announce that the harvest will be that we again will find bases of orthogonal functions, and now in part 2 I will show a few applications of that. And of course the whole episode will end with a summary and a discussion. So, Let's go for it. So we will have an intermezzo now. The pencil and paper study of the proof of self-adjointness, trying to push the boundaries and relax the conditions a bit. So I will find myself a clean sheet of paper and we will work it out with the pencil and paper, and I will talk you through that. Afterwards we meet again and summarize our findings. So we are going to investigate where exactly the conditions, under which conditions exactly we have self-adjointness. Self-adjointness is a kind of a property of a context as a whole. So we do have a linear differential operator, and Sturm-Liouville theory considers differential operators that can be written in this form. So the derivative with respect to x of the derivative with respect to x of the unknown function y times a prefactor p. That function may also depend on x. There's a minus sign there. Plus we add the function y multiplied by a function q of x. So if your differential operator can be written in that form, then it is within the scope of Stur-Liouville theory. So that is one ingredient. And the other is then the property of self-adjointness, that is defined with respect to a bracket that is defined here. So it is an inner product of two functions u and v, and it is defined as being the integral of just multiply u and v with one another and then integrate from the beginning to the end of some interval. And in the earlier section in the textbook, the interval started at 0 and it ended at 1, but let us generalize that a little bit to have a little bit more freedom there. And of course it doesn't matter so much because you can always, by shifting and scaling the variable x, you can always have this interval start at 0 and 1, end at 1. But sometimes it is convenient to have other boundaries, as we shall see. And so there is an inner product defined like that. And then the property of self-adjointness that is key is this one. You say if I have, I can shift about the linear operating acting on an argument function u, and then take the inner product with v. That should give the same as having the inner product of u and L acting on v. So I can move about that linear operator from one argument to the other in this inner product construct. Now, as we saw earlier, that is similar, analogous to having a symmetric matrix sandwiched between a row and a column vector in linear algebra. And that also has this property, but you can read it as acting either first on the first argument or on the second. And given that, if an operator has that property, then you can show that the eigenfunctions are orthogonal. The eigenfunctions that belong to distinct eigenvalues have to be orthogonal if you have this property. So that is the power of having that property of self-adjointness, as it is called. And now we focus on where exactly, under exactly what conditions this holds. Hoping to be able to, first of all, reproduce the conditions that we did adopt already for regular Sturm-Liouville problems, but we hope to be able to extend that a little bit so that we can include differential operators that have regular singular points. So, for example, where p of x would have a 0, especially at the boundaries. So that's the strategy. Now let's see what how we can recover the conditions under which hold, given all this context. Now, first of all, it is convenient to split that linear differential operator in two parts. The easy part is this second part. I just multiply by a function y, and then more complicated is this one. But first of all, what I can easily show is if I do split that, when I start writing the left hand side and then substitute this decomposition, so I say my L actually consists of a first part and a second part, both acting on U, and then we have that second argument V. Because this is an inner product, it is linear in both of the arguments, so that falls apart. This plus see the inner product is linear in this slot, so it distributes over this plus, or you can take it apart and write it like that. Now this one is easy, so I copy this. And now I use the definition of the inner product as we have it over here, with this, and substitute also the definition of. So this is supposed to be an integral, and L2 is just multiplying U by Q. So Q depends on X, and U is also a function on X, and here we have V on X. And the whole thing is integrated. But of course I can move about this Q over there. I can move it doesn't matter a bit. This is just ordinary multiplication of functions, so I can now write it as so, that I say I first multiply V by Q, and then by U, and then I integrate. But this, of course, is U, and then this is the definition of my L2 as I had it. See, on V. L2 on V means that I multiply just L2 on Y means that I just multiply Y by Q, so L2 on V just means that I multiply V by Q. So here's my L2, and then I integrate, and this, again using the definition of that bracket, is just U L2 times V. See, so we see here, compare that L2 has moved from the first slot to the second one. This inner product, this integral is the definition of this inner product. See, so I have two slots, and L2 was in the first slot, but I showed that it is the same. You get the same result if you have it in the second slot. It's rather trivial in this case. So L2 is self-adjoint, and if L1 would be self-adjoint, then I could write for that U in L1 minus L1V, and then take it together again, and then I get U minus L1 OV plus L2 OV and that together is L. See? So that would prove that you can move L from the first slot to the second one using that you can split it because the inner product distributes over the plus, and assuming that L1 would be self-adjoint, so I can move that and then we can put back it together. And I have shown here that it's rather trivial, but it's an exercise in demonstrating self-adjointness for a very simple one. What you have to do is show that you can move, just using the definitions of everything that is given, that you can move the L2 from the first slot to the second one. And we have shown that that is possible. So, but the key point apparently is to show this, that L1 would be self-adjoint. Well, that is less trivial, because L1 is a less trivial operator. It is over here. So we have to investigate that one. Under what conditions would that differential operator, that it is, L1 be self-adjoint? So we concentrate on that, and if that is guaranteed, then L will also be self-adjoint. Now there we go. So we just have to, all the ingredients, everything that is given is on paper. So we just go and investigate under what conditions could we move L1 to the other slot. L1 is this, and the minus is just a multiplication by -1, so that would not have an influence on the self-adjointness. So here we go. To say, well, the goal is to show that L1, to investigate under which conditions we could move L1 from the first to the second slot in this inner product. Of course, we need to make use of all the definitions that we have. First of all, I write the definition of the inner product. That is that integral from A to B. And then I have to write L1 working on. So that is the derivative with respect to x, bx, and then the derivative of u with respect to x. It's clear that u is a function of x, so I don't take that into account in my notation. So that is this, L1 on u, and then you have to multiply by v, depending on x, and integrate Ox, that is this part of the definition. And I'll try to make progress. So I have an integral, so I'll make an attempt to integrate it. It is essentially integration by parts, and integration by parts is essentially using the product rule of differentiation backwards. So what do? I move this parenthesis over there. I say, how about this? If I would write down this, instead of that, because if I would integrate this, I can integrate it. The integral of a derivative is this function itself, and then substitute the boundary. So that is the progress that you expect to make. But of course this is not fully correct, because this is a product, so we have to, if you would evaluate this, you would have to apply the product rule. So you would get this derivative working on this part, which is what we have times that, but also this times the derivative of that. And that is, we don't have that, so we have to subtract it to make sure that what we get is equal to that. So I have to subtract p of x du dx, and then that derivative acting on v, so dv dx. And that whole thing, this is integrated. See? So thanks to the product rule, this is equal to that. The product, if you multiply this product, concentrate on the product that is over there, you get the derivative of this times that, and that is what we had. But you also get this times the derivative of v, and that we did not have, so we have to subtract it. Now it's fine. Now as promised, I can integrate this. This is an integral of this, so I get that, and then you have to substitute the boundaries plus that. So I copy. So you have now integral minus the integral AB P du dx dv dx plus, and then this bound symbol, what is in between the integrand, the derivative, the integrand of a derivative is this integrand. The integral of a derivative is the integrand, and then the boundaries substituted. So we will do that in a minute. Well, that is what we have to do. That is this. And I've written the integral that we are left with over here. Now then again we have an integral, and now to make progress I do the following. Again a kind of integration by parts, a copy of the minus. I write the integral sign. Now I'm working towards L1 acting on V, so I pull this ddx out of this product. And see, so that again I get something. This was a function of x. So again I've pulled this one out, so I get L. dv dx is still here. What is that u? Now, to what extent is that equal to that? Well, I have to subtract what I don't have. What I do get is if this operates on that, it's fine, so I have to subtract. But the rest I don't have, so I have to subtract ux ddx acting only on p and dv dx. See? If you consider that and compare it with this, consider this as a product. The product is over here. If I have this differential operator act on that u, I get that term, dv dxp, that is fine. But if this ddx operates on this combination, that is not what I have over there. So I have to subtract that times that term, minus this, and the derivative of that. Okay. This was an integral, that is that dx. So that closes over here, and here still have that px du dx vx between the boundaries B and A. So you see this term over here, this is actually the L1 ddx acting on the combination P ddx of a function is L1 acting on that function that is multiplied by U and integrated from A to B ddx. So that is the inner product of this U times L1 acting on V. And this minus times that minus is positive. See? So we have succeeded in showing that L1 can be moved within this inner product from the first slot to the second slot, acting on the second argument, provided that this is zero. This and that and this we can integrate. That is a derivative of something integrated. So that is, we have to copy this minus sign. And now we have P of x dv dx times U between B and A. So substitute the boundaries B and A, and we still already had that one, so I have to copy that. P of x again. And this was the U dx times V of x. Substitute the boundaries B and A. Now, I can rewrite this, and the most convenient way to do it is to first concentrate on everything that has to do with the boundary B, and then consider the boundary A. So I copy this result, that is what we hope to establish. So we are after the conditions under which everything that is here is zero, so that we are left with only this, and that would be the self-adjointness of L1. We have to find a way to interpret this to the side under which conditions it is zero. Now, a convenient way to see that is as follows. So suppose we substitute the boundaries B here and there, and then what we get, I copy this minus, and in all cases we get P with B substituted, and then what do I get? I get B in U times dv dx, and I start writing. You will see that it is right. We'll start writing a determinant. So here substitute B, I get U times V at B, V prime. And here I get V, the U dx, but I have a minus here, so I can add a minus, and that is exactly what you get if you calculate the second diagonal of our determinant. So here I have V at B, U prime. So it looks like a Wronskian of the functions U and V. See? That's if I substitute the B's. And now if I substitute A, what do I get? I got P of A and then U at A and v prime at A. And here I get v at A, u prime at A, and I had this sign. Well, this was the lower bound gives a minus. I have a minus there, so this is apparently a plus. And this is a minus for the lower bound, so that is okay. This plus is over there, and substituting a minor bound in as a boundary of an integral gives the minus. Just substitute this and minus what you get from substituting that, and that corresponds with the minus of this diagonal of that determinant. So again we have a Wronskian of u and v, but now at the boundary point A multiplied by the value of that function p at the boundary A. So when is this rest part 0? And if that is the case, L1 is self-adjoint. Well, one possibility is to have these determinants equal to 0, both at the end and the beginning of the interval. And to see when that happens, it says it is a 2 by 2 matrix, the determinant of a 2 by 2 matrix, and that is 0 if the two columns are dependent. And the columns are dependent in two dimensions. If I have just two vectors and they have to be linearly dependent, they are just a multiple of one another. So graphically, if I would make a sketch of the R2, and I sketch two vectors that are linearly dependent, and by this vector u, I mean such a column, so the u prime, that column vector, I call u and I sketch it here. If it is to be linearly dependent, so that should be nicely through the origin, neat vector. If that is to be linearly dependent with v, v should be along this line, v should be a multiple of u. It might be in the other direction, it might have a different length, but the situation of linear dependence of two vectors does look like this. If the column vectors are such that they are one multiple of one another, a scalar multiple of one another, then they are linear dependent, and then this determinant would be 0. But that means if they are along the same line, they are both perpendicular to the same one and the sum, but one and the same vector, and I call that alpha. Say that they would be perpendicular to one and the same vector. If that is the case, then they are linearly dependent, and then this determinant would vanish, and then this would be 0. If I write that, so this would be 0, sufficient condition would be that alpha dot u, and that is alpha 1 u plus 1, or u, the function of u, and by the vector u I had in mind this column. So the second component is the u prime at at A, for example, if I apply it to the first. And that should be 0, and also V. If that holds, so the same conditional V. So both U and V would satisfy the condition that they are both perpendicular to one and the same vector, column vector in the R2, then they would be linearly dependent, and then for sure this determinant would vanish. So that is a sufficient condition at the boundary A, x is A, for this term to vanish, no matter what the value of P is. But these are exact. This just says that, or in other words, that U and V obey homogeneous Robin conditions. These are exactly the conditions that we adopted for regular Sturm-Liouville problems. Weighted sum of the value and the derivative of the function must be 0. So this is homogeneous, must be 0, and it is general. If you would have just this, alpha 2 is 0, then it would say the value of the function must be 0. That's a homogeneous Dirichlet condition at the boundary A. Or the other way around, if alpha 1 is 0, then you say the slope must be 0, the derivative must be 0, that's a Neumann condition. And the linear combination of those is called the Robin conditions, or homogeneous Robin conditions. So if both U and V obey the same Robin condition at x is A, so the starting point of the interval, then for sure this determinant would be 0. Now the same argument applies here, so that would, the Robin condition, to require that the functions U and V obey Robin, homogeneous Robin conditions at the end of the interval is sufficient for this. So the conclusion is indeed that the regular Sturm-Liouville problems that we already studied, that was such an operator on an interval, and at the beginning and the end of the interval we had this homogeneous Robin conditions. So if the requirement is that all the functions that you will work with, the space that is spanned by all the functions that obey homogeneous Robin conditions, and you work with such an operator, then it is self-adjoint with respect to such an inner product. So now we have recovered from this analysis the familiar conditions, the mixed homogeneous Robin conditions at the beginning and the end of the interval, and those are the familiar conditions for a regular Sturm-Liouville problem. So that comes out automatically, but what is so interesting of this exercise is that there's another way. If P would be 0, then it's easier. Then unless, this is very singular, so unless you would have, unless this would be infinite, for example, if the function that can happen, the functions that you work with might be, if they're infinite, then there's a problem. You would have to restudy the exercise and say, well, then if you get infinities, then you consider this as an indefinite integral and take the limit. So you have to take the limit of this argument to B and see if it remains finite and if the integral exists in the first place. But if it does, And if it can happen if p is 0, that limit is 0. And if these functions are finite and differentiable and have a finite derivative, so that this determinant is finite in the first place, then for sure, if p has a 0, then the condition that this term must vanish is automatically satisfied. And that's very interesting. So if p vanishes at x is a and x is b, so at the beginning and the end of the interval, then the corresponding term here also vanishes automatically, easily. If I label this boundary term, provided are not too singular. So that's something that you might have to investigate in practice if you work with a certain problem. Investigate if this is if it is singular and how bad it is. But sometimes it's easy if you just require, I want to work with only the non-singular solutions of a problem, then this is certainly 0 if p has 0. So that's so interesting because p is 0 corresponds, if you write it out, that you get px, second order derivative of y, so p is the coefficient of the highest order derivative. If that has a 0, then you have this. Then you have that at that boundary point, the condition for self-adjointness is easily satisfied automatically. And those are the regular singular points, and that makes this so interesting. So the regular singular points that we met in chapter 5, and what happens there can be diagnosed by the Frobenius theory. That allows you to figure out if the solutions at those points remain finite, and if they are singular, how bad it is. So the Frobenius theory allows you to figure out what solutions a differential equation has, the eigenvalue problem value for L, viewed as a differential equation. Frobenius theory of chapter 5 allows you to figure out what kind of solutions there are. And the regular singular points are special in that they, for the non-singular solutions, they guarantee that these conditions for self-adjointness are satisfied. So you see that the regular singular points of chapter 5 have a kind of a tendency to generate orthogonal sets of solutions, orthogonal bases, in this sense. So now you see that there's a kind of a thread in the course to focus on regular singular points. In chapter 5, where we already discovered that they were important in many applications because equations that have those regular singular points show up. For example, in chapter 10, if you do separation of variables in spherical or polar coordinates, you have such equations that have regular singular points. And now we see that those points tend to make the differential operator in the context of such an inner product and in the context of functions, solutions functions that are sufficiently well behaved, so they don't go very aggressively to infinity. The function values and the derivatives, those in such a context, L has a tendency to be self-adjoint, so you can expect if you have regular singular points and you integrate between regular singular points, you can expect to find orthogonal functions. We will see a very nice example of that is Legendre's equation, so that we shall have as an example of this. That's a very nice one. So welcome back. Let me close this part 1 of this episode by a summary and a brief discussion of what our findings were with pencil and paper. So we did find an option to extend the Sturm-Liouville formalism. We can allow now boundary points of the interval which the problem is defined to be regular singular points of the differential operator that is central to the Sturm-Liouville problem. So that can now be a Fuchsian differential equation that has regular singular points. And as we saw, revisiting the proof of self-adjointness, in practical cases, but you have to study them case by case, carefully checking the proof and checking if you can, how and if and how you can meet the conditions for self-adjointness. But it is in practice usually often possible and even natural to have self-adjointness as a consequence of rather natural restrictions on the functions. For example, we require the functions that we want to work with to be bounded, so to not go to infinity. And we impose those restrictions on the functions that we shall allow in to emerge as solutions or as functions that we work with in the first place. Now, why is that natural? Well, not from a mathematical or logical point of view, but from an engineering point of view, or applied sciences point of view, or physics point of view. That is a natural condition. For example, if we would work with the gravitational potential with Legendre's equation, then the regular singular points would correspond to the north and south pole of a coordinate system for a planet. Now, it's no surprise that those are regular singular points, because the coordinate system is special there. One of the angle, the longitudinal angle, is kind of undefined. For all angles, you remain at the same point at the pole of the coordinate system. So it is no surprise that there is a singular point in the mathematics there, but physically, from a physical point of view, we know that the gravitational field does not have an infinity there. Force doesn't become infinite or anything. So often from an application point of view in physics, it is natural to just put the conditions that, well, mathematically there can be singular solutions, but physically we work only with the non-singular solutions. Now, in the context of the formalism, the restrictions are conceived as boundary conditions at the regular singular points of the differential operator. So the points at which you impose the conditions emerge very naturally from the differential operator that we are working with. The conditions themselves also are natural, as I just discussed. the fact that we call them boundary conditions may be not so natural, but that is to make the connection with the Sturm-Liouville theory as we had it from regular Sturm-Liouville problems. And we chose to define some interval ourselves. There was no special reason for it. Apart maybe because you are working with a string or a bar of heat diffusion or something like that. But from the point of view of the differential equation itself, those points were not special. But here they are. Now we have regular singular points for the differential operator, and then those points are special, and it is kind of natural to have conditions imposed there. And to make the connection with the general Sturm-Liouville formalism, we call those boundary conditions. But they are rather mild. They are rather mild conditions. It's not that we prescribe what the value or the derivatives of the functions should be at those points. Usually we only prescribe that they must not be infinite. Guided by the details as we saw it when we carefully studied the proof of self-adjointness, so the conditions that you need to obey, such as to have self-adjointness. And from the proof, again, it is also obvious and clear that it is really the regular singular points that play a role there, because it is the function p, which is the coefficient of the highest order derivative. If that has 0, which is the very definition of a regular singular point, that is exactly what helps to obey the conditions for self-adjointness. So you see, everything nicely fits together. So we have a nice connection. Now the harvest is orthogonal basis consisting of eigenfunctions. All of that is profitable. To have an orthogonal basis, it is very profitable because that makes it easy. To have a basis in the first place makes it possible to expand functions in terms of the base functions. That the basis is orthogonal makes it easy. Then you can use the projection formula to calculate the coefficients. That there are eigenfunctions is also very profitable. It means if you substitute the expansions, and as soon as the eigenfunctions are substituted in a differential operator, so the left-hand side of the Sturm-Liouville problem, there are eigenfunctions, so all the differential operations and multiplications by functions all reduced to just a multiplication by the eigenvalue, which is just a number. So the problem usually simplifies very, very substantially because you work with eigenfunctions. So all of these keywords in this simple one line, rightfully we can call that a harvest. This was all very profitable to have. Now, as I just said, given suitable restrictions, the orthogonality can result from the regular singular points. So it is really a consequence of having regular singular points, so that it's a very nice discovery, I would say, that the regular singular points that played the main role in chapter 5, and that was the very reason why we studied the Frobenius theory. Those meet Stur-Liouville theory because they play the key role here in having these orthogonal bases of eigenfunctions. And it also emphasizes how profitable it is to have the Frobenius theory, because that allows you to develop a diagnosis at the regular singular points. How many solutions does the differential operator have, and which of those are singular, and which of those are non-singular. So all that kind of things you need to know to make an inventory of the situation that we have here with these Stur-Liouville problems. So I would say that it's quite quite a nice harvest, and so that is also a good point to end this first part of this episode. And then we continue in part 2 by considering a nice example.